Hello, this is Pat Hindle, Technical Editor at Microwave Journal, and it's my pleasure to welcome you all to this session in our Microwave Journal Technical Education webinar series entitled An Overview of FEKO Suite 7.0. Before we start, there are a few questions that I would like to, items that I'd like to bring to everybody's attention today. Your presentation will be approximately 45 minutes long, after which time we'll hold a Q&A session. You may submit a question through the website at any time during the presentation through the Q&A box. We will hold the questions to the end. Please make sure you address your questions to all panelists, which is the default setting in the Q&A box. This presentation will be archived and available for viewing later on in the events section of the Microwave Journal website. Also, if you'd like to see any more detail on the slides, you can click on the enlarge button in the lower left-hand corner. FEKO is a leading comprehensive electromagnetic simulation software suite, widely and intensively used in many industries. It is helping its users to reduce product development costs, to accelerate the time to market, and to optimize the performance of products and applications. This webinar will give an overview of what is new in the release 7.0, and we'll be introducing an offering soon. The webinar will cover, among other things, new methods and techniques, features, applications, the workflow, and examples of how users will be able to work with it and take profit for the new release. At this point, I would like to introduce our presenter today. Dr. Jordi Soler is the Global FEKO Business Development Manager at EMSS. His history with EMSS began in 2000 as a FEKO user for over 7 years. Later, in 2009, he started working with EMSS as a FEKO reseller for Spain and Portugal. During the last 17 years, Dr. Soler has occupied several business and engineering management roles at different international pioneering technology companies that develop and market innovative products mainly related to electromagnetics, antennas, electronics, and semiconductors for many different industries. He's won several awards and is co-inventor of 20-plus antenna patents involving in licensing deals over $41 million. So at this point, I'd like to hand over the session to Dr. Soler.
Okay, thanks for this introduction. Hello, everyone. Welcome, and thank you for attending this webinar. My name is Jordi Soler, and I'm acting as FEKO Business Development Manager. The goal today is to give you an overview of the main features you will be able to enjoy in the new FEKO release, Suite 7.0. We have split this webinar into the following topics. We will start with a snapshot of how FEKO is positioned today in the market, with a brief introduction of how to work with FEKO and which are the main graphic user interface components. Next, we will show you and explain the simulation map of the FEKO solvers, and we will explain some of our solvers to you through a set of examples. Later, I will talk about a set of productivity features like the cable analysis tool in FEKO or the modeling of arrays of antennas, among others. The last items before concluding this webinar are focused on CAD import-export filters, CAD Healing Tools, high-performance computing in FEKO, and on considerations around pricing and licensing. Also, during the webinar, we will make 2 polls, and we will ask you to answer them, of course, if you want. Now, if we briefly talk about industry sectors, today FEKO is widely and intensively used in many industries, being some of the most important ones: automotive, aerospace, defense, naval, communications, electronics, and healthcare. FEKO is being used in these industries for developing new products more and more in the early stages of the product design cycle, since companies want to reduce unnecessary prototyping costs, detect and fix potential issues and problems in the first phases of the design cycle, and accelerate the time to market. Also, FEKO has become a virtual test platform for scenarios where measurements of the actual usage environment is challenging and costly. And last but not last, it is also worth mentioning the powerful program and facilities we give to the academia. Now, if we talk about applications, some of the most well-known and key applications for FEKO are related to antenna design, antenna placement, scattering analysis, cable coupling, electromagnetic compatibility, radome design, and RF design and safety, working from very low frequencies, hundreds of hertz and kilohertz, up to very high frequencies, 100 gigahertz or higher. And how do we work with clients and potential new clients? We do think it is very important and key to work closely and together with our clients, and we are organized so we can provide an outstanding service and technical support to clients at a local level. In the map you have in black our offices and in blue our distributors. Another aspect we pay special attention to is the user workflow and interface, and FEKO is developed to be easy to use, intuitive, and integrated. In the workflow, there are three main components. We have CADFEKO, the FEKO solver, and POSTFEKO. CADFEKO is our preprocessing environment for geometry modeling, where to set up the solution and from where to launch the FEKO solver. And POSTFEKO is our post-processing environment. Now, if we talk about the FEKO technology and solvers, at EMSS we believe that no single method is capable of solving the whole spectrum of problems, which is why different methods are normally applied to specific applications. Here you can see our simulation map with different kind of applications and problems, positioned in this map according to their electrical size and to the complexity of the materials involved in these problems. And in FEKO we have two sets of solvers. A first set of full wave methods, which are a physically rigorous solution, and a second set of asymptotic solvers, which are high-frequency approximation. And depending on the problem you want to target, you need to select one method or the other. And it is also important to highlight that we have hybridized some of these methods in order to solve large and complex problems. The last additions to our set of solvers are FDTD, indicated in this blue rectangle, and the hybridization between our multilevel fast multipole method and the physical optics solver, indicated with this green arrow you can see here. Whereas FDTD is more focused on the analysis of problems with complex dielectrics, for instance, dealing with inhomogeneous dielectrics, being these problems not very big in terms of the wavelength, the new hybridization between MLFMM and PO is especially suitable for the analysis of very large structures. The first method I would like to cover today is related to the replacement of the traditional method of moments by a fast integral equation solver, MLFMM, for the analysis of big structures. We first released MLFMM in 2004, and basically MLFMM groups basis functions and computes the interaction between groups of basis functions rather than between individual basis functions as done with the method of moments. And here you can see that with the method of moments, memory requirements scale with a square n, and with MLFMM, they scale with n log n, being n the number of unknowns. And in terms of runtimes, we have that with MLFMM, we have a dependency of n log square n, and with MOM, this dependency is n to the power of 3. And this is translated into huge memory and runtime savings. This is an example where we compute the antenna parameters at a high frequency in a large chip with 10 million of unknowns. With a single one-core CPU, one would need about 1,500 terabytes of memory and more than 1,000 years to solve. Although it is true that by using a modern cluster with enough memory, one might be able to solve this problem by using an intelligent method like MLFMM. One can solve the problem in less than 2 hours with 66 gigabytes of RAM. And now we have included an example related to the automotive industry, and where we want to show you how FEKO permits the user to get accurate and fast results with electrical sizes varying from from several to hundreds of wavelengths. We used a detailed CAD model of an OutDTT containing about 500 parts, and here we account for the metallic parts of the body. Although in FEKO, of course, you can also include the dielectrics. And here we have the antenna on the roof of the car. As working frequencies, we work from 450 megahertz up to 20 gigahertz to cover systems including push-to-talk, Bluetooth, wireless LAN, and ultra-wideband. All the simulations were run on the same cluster. This is a 2 quad-core Intel Xeon CPU, so with 8 processes in total and with 72 gigabytes of RAM. And in the following table, you have first column, you have frequency, then you have the electrical size of the car, length, width, you have the number of unknowns, big memory in gigabytes, runtime in minutes, and here you have the method that has been used. Firstly, we would like to highlight which are the typical electrical sizes of the car, depending on the frequency of operation. Here, for example, if you look at the length, you can see that they are from 6 lambdas up to, for this case, 270 lambdas. And secondly, by looking at peak memories, runtimes, and the method used, and for this particular case, one can see that you can use method of moments here for up to 1.8 gigahertz, MLFMM for 1.8 up to 5.2 gigahertz, and PO for the higher frequencies. And with a good agreement with the different solvers, and as can be seen in the next slide. Here you have 2 CADs of the total gain at 1 gigahertz using MOM and MLFMM. MOM is plotted in blue and MLFMM in green. This is the horizontal CAD, and here you can see the vertical CAD, and you can see there is a very nice agreement between the 2 methods. We have prepared another example for you where we will be showing you the benefits of using some of the other methods, and in this case for the analysis of radomes. FEKO is also widely used for the analysis and design of radomes across many industries. A radome is a structural, weatherproof enclosure that protects an antenna, which is constructed in several shapes depending on the application. Some factors affecting the performance of a radome are the radome wall thickness and design, its shape, and the materials used for the radome. Based on the wall construction, we mainly have 2 types of radomes, monolithic or single layer and sandwich design. 2 of the main uses of FEKO in connection with radomes are, the first one is the characterization of the material of the radome, and the second one is related to the analysis and design of the radome. And depending on the electrical size of the radome, you should use one method or the other. Now we show you an example of a monolithic thin wall radome having a permittivity of 4 and a loss tangent of 0.015 on a dipole array working at 9.4 gigahertz. The radome has a height of 10 lambdas and a radius of 5 lambdas, and since this is electrically large, we treat the radome with ray-launching geometrical optics, or RLGO, which is a ray-based technique that models objects based on optical propagation, reflection, and refraction theory. To compare the results, we have also analyzed the same case with MLFMM. And in this graph, you have the ray antenna without radome in red, and the antenna with radome analyzed with MLFMM in blue, and analyzed with RLGO in green. Two of the changes that can be produced by radomes are the radome insertion loss, radome loss, and the bore-side error, also called BSE. Here we can see that the radome is introducing a loss of 1.2 dB and with a negligible or zero bore-side error. We can also see that there is a pretty good agreement between MLFMM and RLGO, and on the bore-side direction, the difference between the two methods is 0.3 dB. But what is the difference in terms of computational requirements between MLFMM and RLGO for this particular case? Here we have a table where you can see a method, the mesh size with in terms of number of triangles, the required memory, and runtime. And you can clearly see the huge savings you have in terms of memory when you are using RLGO, and also that runtime in this case is reduced by a factor of 4, which is a nice example of to show the benefits of RLGO for the analysis of radomes. Next, if we talk about the new hybridized method, MLFMM PO, in 1992 we introduced the hybridization of MOM with PO, and in 2004 MLFMM, as previously said. Now with FEKO Suite 7.0, we're introducing the hybridization of MLFMM with PO to solve extremely large structures, and where MLFMM is used to model the complex part of the structure, these are fine details, sources, and PO is used to model the smoothly varying part of the structure. Also, it is worth mentioning that in FEKO, we have the large element PO solver, which is an alternative set of basis functions for the PO, which allows us to have mesh sizes of multiple wavelengths. This leads to huge computational cost savings, and in the cases where LEPO can be applied. And we have also implemented the hybridization between MLFMM with LEPO. We will explain you this new iterative method using an example of a horn antenna and a reflector. You have the horn antenna here, which is modeled with MLFMM, and here you have the reflector, which is modeled with PO. Also here, JMOM stands for currents on the MLFMM region, and JPO for currents on the PO region. And for you to better understand how this coupled method works, we now briefly explain to you what is the iterative process that we follow. First, we initialize the PO current to 0. We compute the MOM current using MLFMM. And afterwards, we use the scattered magnetic field caused by the MOM currents to compute the PO currents. Then the scattered field caused by the PO currents radiates back into the MOM region, and we modify the right-hand side vector of the iterative solution. With this new right-hand side vector, the process from step 2 is repeated until convergence is reached. Now we have this example where you have here a waveguide horn with about 7,800 unknowns, and also a reflector that has a diameter of 36 lambdas. We have included here the simulated gain versus the theta angle with MLFMM in blue and with the new hybrid method in green. And you can see that there is a very nice agreement and that only there are a small deviation in this angle. And here we would also like to show you why it is important to take into account the coupling between the two methods. And to do this, in the next slide, what we have done is compute the gain of the antenna versus the angle. Again, you have the results with MLFMM in blue. And in this case, in red, you have the results when you are using the method of moments with PO, but being these methods decoupled. And here you can clearly see that this is a case where it is important to take this coupling into account. In terms of computational requirements, here you have a table where you have the unknowns for the MLFMM, the same but for the PO, big memory, and runtime. And one can easily see that with MLFMM PO, we require 16 times less memory, and it is 40% faster for this problem. And without forgetting that if we would like to use the hybridized MUM PO solver, it would take days to solve. Finally, also regarding MLFMM PO, when you have the chance to play with the new release, you will see that it also converges fast. Only a few outer iterations are needed. Typically between 3 to 5 iterations are needed. And up to this point, we have been talking about methods and examples related to the frequency domain analysis. However, with FEKO, you can also perform time domain analysis. With FEKO Suite 6.1 and older versions, a user had to request the required results on the frequency domain and could select the frequency domain solver in CADFEKO, and afterwards see the results also in the frequency domain on POSTFEKO. Later, when we launched Suite 6.2 and also with version 6.3, the time domain analysis support was implemented in POSTFEKO, replacing the old TimeFEKO component. Support for time domain modeling was included not using a time domain solver, but with intelligent FFT and inverse fast Fourier transform conversions that are hidden to the user. These allowed all methods such as cable coupling, PO, MLFMM, MUM, the finite element methods, and the planar wind function to be readily available. And in FEKO Suite 7.0, we're adding a finite difference time domain solver to be able to perform time domain analysis in a way that the user needs to make the request on the frequency domain, enable and launch the time domain solver, get the results on the frequency domain, and with the possibility to show the results on the time domain via post-processing in POSTFEKO. And in future releases, we will add time configurations so the user can make a time domain request in CADFEKO, select the frequency or time domain solver, and get the time domain results directly in POSTFEKO without requiring any post-processing. And also in future releases, users will also be able to represent native time results in frequency via post-processing in POSTFEKO. And if we talk about the workflow for FDTD, you will see that it is easy and straightforward. In CADFEKO, we have what we call multiple configurations, which provide users with the option to obtain multiple solutions for a single model. And for frequency domain results, you need to create a standard configuration and then just go to solver settings, to the FDTD tab, as you can see here, and you just need to select to activate the FDTD under solver settings. On the other hand, for time domain results, the workflow is basically the same. You have to create the standard configuration, activate the FDTD under solver settings, and then you need to perform the time analysis in POSTFEKO. From the different examples we have for FDTD, we have included here for you one which is related to the analysis of an electromagnetic pulse, also called EMP, on a two-story building. This is a scenario where making field measurements is challenging. And here we want to investigate the transient fields caused by the EMP. This example came from a customer interested in investigating how to shield electronic equipment in hospitals to protect them against electromagnetic pulses. The building structure is simulated with FDTD using a typical pulse, and the results are cross-validated with the frequency domain method of moments at specific frequencies within the spectrum of the pulse. Here we are showing you some simulated results. Here you have the electrical near field with FDTD in red, and for method of moment in blue at two different positions. And you can clearly see that the results agree extremely well. And also you can see this agreement by looking at the near field distributions. You have the magnetic field on the first row. You have here method of moments and FDTD. And you have the same plots, but for the electric field on the second row. And you can also see that there is a very nice agreement between them. And in terms of computational requirements, here you have a table where you have method. This is the MOM using the surface equivalent principle and FDTD. And you have the required memory, runtime in hours, and the characteristics of the machine that has been used to perform the simulations. In this case, we can see that by using FDTD, we can reduce the memory requirements by a factor of 9 and runtime by a factor of 7. We have also included another example for you for FDTD, which is related to healthcare, and in particular in connection with human phantom modeling. While method of moments offers a superior computational efficiency for design, working with homogeneous phantoms, up to now we had the finite element methods to model inhomogeneous dielectric bodies. And also in 2005, we hybridized method of moments with FEM, and in 2010, MLFMM with FEM to take profit from both methods in the same problem. Now, with FEKO Suite 7.0, we can also solve inhomogeneous dielectrics with FDTD, as well as with the hybridized method using method of moments and FEM, which offers a clear advantage for the user to cross-validate simulated results for applications where obtaining measurements is complex and costly. Here we have the simulated electrical near fields and the specific absorption rate, the SAR, for an anatomical head model with 8 tissues at 300 megahertz. We have the results in the first row for MOM-FEM, and in the second row you have the same results but using FDTD. Also, I would like to point out that we are now extending the Phantom model database thanks to our collaboration with Simpleware and their human body models. And on June the 18th, we will be giving a webinar. We'll touch on healthcare applications and where you will be able to know much more about this. And having said this, we will now move on to a new section focused on a set of productivity features you can also find in FEKO 7.0. But before doing that, we would like to do a brief poll that you should now be seeing, which is related to which of the following solvers you are mainly interested in. And we would really appreciate if you could answer this poll, of course, if you want, and we will give you about half a minute to answer this poll. Thank you. Okay. While you are responding the poll, I will start with this next section about productivity features in FEKO. And the first features we'll be talking about is related to cable analysis. Many problems of electromagnetic compatibility and interference involve cables, which either radiate through imperfect shields and cause coupling into other cables, devices, or antennas, or which receive external electromagnetic fields radiated from antennas or leaked through other devices, and then cause disturbance, voltages, and currents, potentially resulting in a malfunctioning of the system. FEKO is used for the analysis of cable coupling problems in several industries, including aeronautics, naval, automotive, and space. The cable coupling tool we have is fully integrated into FEKO, where here you can view a screenshot of the cable schematic view. It supports many different types of cables, shields, and also the importation of KBL files. Cable paths can be loaded, excited, or connected using SPICE circuits, and cable probes can be placed along the cable. Also, it is worth mentioning that there is full support for S-parameter calculations in connection with cable ports. If we talk about solution methods, we have the standard multi-conductor transmission line MTL technique and the combined method of moment with the MTL. Whereas the MTL technique requires a current return path directly beneath the cable harness and that the cable must be electrically close to the ground, the combined MOM MTL technique works for cases where the cable does not run close to ground and can handle gaps in conductive planes. With these methods, one can make the solution of virtually any cable and ground plane environment possible. We can work with arbitrary cable cross-sections due to a 2D static firm solver that calculates the RLCG per unit length parameters. You can do radiation requests. This is radiation due to the cables into other cables, antennas, or other devices. And also you can do irradiation requests, which is related to the coupling of external fields into cables. And finally, you can, in the same problem, you can just do radiation while taking irradiation into account. We want to show you the following example related to the automotive industry, where EMC and crosstalk are major concerns. Here we have a vehicle with a cable connecting the control electronics in the engine to the taillight assembly, and also we have a 3G booster antenna on the rear roof. Here we would also like to point out that while individual systems may appear to be safe, problems may arise when the complete vehicle is analyzed. And related to this, FEKO is assisting engineers in exploring design and analysis scenarios to ensure automotive EMC regulations are passed. And here we want to know how much energy couples into the cable when the 3G antenna is transmitting, and how much energy is coupled to the 3G antenna when signals are transmitted through the cable. To do so, we define the cable and shielding, we route the cable, connect the cable elements, and we then run the solver. The results you get in POSTFEKO are as follows. Here you have, for the radiation request, you have the induced voltage at antenna terminal, which is the cable signal coupling to the antenna terminal. Here you have the voltage versus frequency. And at the bottom left, you have here an example of the near field radiated by the cable in a plane. And next to it, you have the currents induced to the body due to the radiation of the cable. If we look at the irradiation, here we can see the induced voltage at the tail light, and this is the 3G antenna coupling to the cable terminal. You have again the voltage versus frequency. At the bottom left, you have in this case in this plane the electrical near field near the cable path due to the antenna, and on the right you have the surface current distributions due to the source. Another feature we have in FEKO, partially related to the automotive industry, is the windscreen antenna modeling, which is based on the method of moment solution. With this solution, you mesh only the metallic windscreen elements, and we consider the boundaries between the electric layers of glass. Also, we consider the coupling between closely spaced antenna elements. You have finite-sized windscreen that can be curved or rotated, and also you can deal with multiple windscreens. You can also enable MLFMM for the windscreen analysis, and you can use our curvilinear mesh elements for the windscreen reference geometry. Here you can see the windscreen tab that is on CADFEKO, because FEKO is developed to be intuitive and easy to use, and following these criteria, you can see now this tab where you have different definitions. You have here this first group where you have the different definitions of the windscreen. The second group is related to the preparation of the surface, and the third group is related to the creation of the surface curves. And this option that we have here, the constraint surface, allows you to use a curved surface as the basis and define a parametric construction space from a 2D plane where to easily construct lines and widths of lines. Many automotive companies are using this feature today, and it is also worth mentioning that these features can be used for the design and analysis of conformal antennas, also for other purposes and other applications. And having said that, now I would like to show you a couple of features which are especially suitable for antenna arrays. The first one is the usage of the periodic boundary conditions, PBC, for the analysis of the radiation pattern of arbitrarily large arrays. With the periodic boundary conditions, you simulate a single element of the array and then compute the pattern of the array by using periodic Green functions. Here you have an example with an array of 21 by 21 helix antennas, where you can see that there is a huge saving in terms of the memory when you compare MLFMM with the periodic boundary condition method. The other feature we want to show you today for antenna arrays is related to the domain Green function method. This is a fast array solver which is very efficient when applied to large finite-sized arrays and cutters for regular or irregularly spaced arrayed elements. Each individual element may be fed with appropriate magnitude and phase excitations that do not have to follow any pattern. Also, self-coupling and mutual coupling are taken into account, and the edge effects of the finite array are accurately modeled. Here you have an example of an irregularly spaced horn antenna array. On the right, we plot the simulated gain versus angle, in blue for the method of moment and in green for the domain Green function method, where you can see an excellent agreement. And at the bottom left in the table, you can see the huge memory savings and also the reduction in runtime. The next feature we would like to mention now is related to CMA. CMA stands for Characteristic Mode Analysis and consists of the numerical calculation of a weighted set of orthogonal current modes that are supported on a conducting surface similar to waveguide modes. And why this is useful? Because it allows for a systematic design approach. It provides you with physical insight regarding the antenna operating principles. You can also determine the resonating frequency for specific modes. And last but not least, it helps you to determine the optimum feeding arrangements to excite these modes. And if we talk about the determination of the optimum feeding arrangements to excite the desired modes, we have here an example. This is a screenshot from POSTFEKO showing the surface currents of one of the characteristic modes using CMA, and here without any source, from where one can investigate and determine the most suitable positions for the antenna to have a specific radiation pattern, for instance. This is an example of an aircraft, but this is also especially suitable for the antenna design on placement on mobile phones and wireless devices. And the last productivity feature we would like to show you today is related to scripting and automation. Lua is a powerful, fast, lightweight, embeddable scripting language used in a wide variety of industries. In FEKO, it is used to extend the built-in functionality or to automate repetitive or complex tasks. Lua Scripting is available in CADFEKO and POSTFEKO, and we have two types of scripts. We have the API scripts, application programming interface scripts, where you can create customized dialogue to obtain the user input. You can also interact with external applications and also the operating system. And it can be used as plugins that extend the application functionality. And the other type of a script is the math script, which is used for advanced data processing. These scripts can be added to CADFEKO and POSTFEKO ribbons. And here we have two examples where we are extending the user interface. The first one is related to a custom dialog in POSTFEKO, where we ask the user for a set of information related to the radiation hazard heises surfaces to be calculated in POSTFEKO. And the second example is related to the launching of Obtenilab from CADFEKO. Obtenilab is a novel, easy-to-use matching circuit generation and antenna analysis software, which includes automatic impedance matching tools and antenna bandwidth estimation. You can call Obteni from CADFEKO, get the antenna automatically matched in Obteni, and afterwards easily return to CADFEKO, where the data of the matching circuit is automatically imported. With Lua Scripting in POSTFEKO, one can also calculate and plot which are the radiation safety zones based on any radiation hazard standard. In this example, we first compute the radiation levels of each transmitter, and afterwards, with Lua Scripting in POSTFEKO, we compute the percentage contribution for each monopole, some percentage contributions. We render the isosurfaces of maximum exposure boundaries and also render field planes where coloring represents exposure levels. This is another example, but not related to RCS, rather cross-section of a missile. In particular, we use the Lua script in POSTFEKO to implement the formula you can see at the bottom, required to obtain an inverse synthetic aperture radar image, ISAR, which is a 2D image of a target. And now, before talking about the CAD import, export, and CAD Healing Tools, we would like to make another poll. And this poll is related to which of the following productivity features you are mainly interested in. Here you can choose, of course, if you want to answer, you can just choose between cable modeling and analysis, which is something that we have already briefly explained to you now. Also, you can choose windscreen antennas, fast solvers for large array antennas. You also have characteristic mode analysis, or CMA. And also, if possible, we would like to know if you are interested in Lua scripting. And as in the previous poll, we'll give you about, let's say, half a minute to give us your feedback. Okay, thank you. Now I will show and continue with this new section. In CADFEKO, we do have a large number of import and export filters for CAD files, which are available for our different licenses. And these are included at no additional cost, which means that you do not need to pay for each filter. And in terms of import and export filters, if we look at the formats, here you have a list of the different formats you can use to import and export geometries, and also the same but for meshes. The most recent additions we have done are related to the formats ODB++, 3DI, and Gerber, which are PCB file formats, and here they are marked in green. Some of our customers requested to have them available, and now with Suite 7.0 they are available. Here we have included an example of a PCB from a client of ours imported into CADFEKO using ODB++ on the left, and on the right you have the surface currents on the PCB, also including an antenna. And if we talk about CAD Healing Tools, first we would like to point out the following. A faulty CAD is a barrier to entry into the electromagnetic simulation environment, and you can have problems, for example, the inability to create a mesh. You can have a mesh with discontinuities or a mesh which is very inhomogeneous. You can also need a necessary extra runtime, and also this can lead to inaccurate or wrong results. And here we'll also like to highlight that model and mesh created for mechanical simulations is different from the model and mesh that one requires for the electromagnetic simulation. And going more into the detail, as healing tools in CADFEKO, here you have a screenshot of the transform tab in CADFEKO, where we mainly have two groups. First group for repairing, and a second group for rebuilding. And these tools are used to correct common CAD errors. They are best applied directly after importing a model. They operate on primitive parts, and in some cases you may need to apply other tools you have in CADFEKO to get a usable model. And also, if you click on the repair part and you go to the advanced view mode, you get the dialog you have here when you can see some of the different options we have. And with the repair part tool, you can remove and repair common geometry faults to create a valid solid. And here, for example, on the right, you have geometry before repairing it, and the geometry you get after using the repair tool we have in FEKO. Now we will be moving to another section, which is devoted to HPC in FEKO, which is high performance computing. It is not always necessary to use full wave methods on a large cluster to solve problems, since one can consider using some of our intelligent solvers or a hybridization of solvers. However, in cases when you may want to solve electrically big and complex problems, which may have complex dielectrics with multiple reflections, one may need to use MLFMM on a large machine. This is one of the reasons why we have been supporting since many years ago message passing interface MPI-based parallelization for distributed memory systems for all our solvers, supporting multi-core, multi-CPU, and cluster-type environments. Here we would also point out that these features are not easy ones. If one keeps in mind that for each method, the problem is broken into several phases. For example, for the MOM, you have the matrix fill, the matrix solve. You can also have the near field calculations. And one needs to address these efficiently to avoid bottlenecks in the HPC environment. Also, there is typically a compromise between communication and keeping data locally. And for environments where you can easily access the memory, we added already in FEKO Suite 6.0 in September 2010 for certain algorithms shared memory parallelization based on OpenMP, where single process creates multiple threads at certain phases. Memory is shared between the threads. There is no duplication of large data sets. And also, larger MLFMM problems can be solved on the same hardware. Since also 2010, we do have a hybrid strategy where you can use and combine MPI for the communication between nodes in the cluster with OpenMP for the parallelization inside of the different cores or CPUs hosted in the same physical machine. And to show you the benefits of this offering, we show you now a simple example. We use a cluster with 6 nodes, having each node 2 cores, and we measure the results using 12 MPI processes, which are non-threaded, and 6 MPI processes, 1 on each node, and using 2 threads each. We have this simple example considering a PC plate with 24,000 unknowns analyzed with method moments. And here you can see how runtime can be reduced by using the hybridized strategy. Another similar example, but now using MLFMM, is shown here, where we have 93,000 unknowns. And one can see in this case that not only we can reduce significantly the runtime, but also there is an overall memory reduction when you have 2 threads sharing memory. And also, if we talk about MLFMM, we have a robust and a stable solution, and we would like to show you some results about its efficiency considering a problem with 3 million unknowns. In this chart, we have the total runtime efficiency, including all the phases in the solution, versus the number of processes. Here, 100% is perfect. And you can see that up to 20 processes, the efficiency is higher than 80–90%, which we think is really an excellent result. Another feature with respect to HPC, and here we'd like to talk about the GPU acceleration. GPU has become very popular thanks to NVIDIA devices based on the CUDA architecture, since these devices include hundreds of cores. We do support GPU acceleration in several of the solution phases, like the LU decomposition of the method moment systems of linear equations, for instance. You can also use several GPUs for sequential runs in FEKO, and we are working to extend the GPU support to other solvers phases with MPI and also for the right launching geometrical optics solver. And regarding the performance of our implementation for the GU acceleration, here we have an example of a radar scattering from a metallic object at single frequency analyzed with MOM. In the graph, you have the performance in gigaflops, billion floating point operations per second, versus number of unknowns for a problem with sizes ranging from 2,000 to 20,000 unknowns. You can see that with an Intel Core i7 with 4 cores, the performance leverages at about 150 gigaflops. And when one uses 1 Tesla GPU and FEKO 6.2, the performance is significantly improved. And in the blue curve, you can see that we reach 700 gigaflops. And moreover, we also introduced, as mentioned before, the possibility to use several GPUs. If one uses 2 GPUs, the performance is even improved, I would say almost doubled, up to 1,300 gigaflops, as you can see here. Next, and if we talk about pricing and licensing, we have several options. We have the FEKO Lite version, which is free, but limited in solving capabilities, but it is good to get to know the basics. You need to register for free if it is used for more than 30 days. Then we have our standard full evaluation license, which is available for 45 days, and you can ask for it on the link you have here. And in FEKO, you can either purchase or rent a license. The bronze license is the most basic license for 32 and 64-bit Windows or Linux systems, where you only have the MOM, the FEM, and also the FDTD solvers, and it is restricted to gigabytes of memory in total. The silver license works with 32 and 64-bit installations, being all the solvers available, and only limited to 2 gigabytes per process. The next license is the gold one, which is for 64-bit systems, having all solvers included and without any limitation in terms of memory. We also have the platinum license. And here we would also like to mention that the silver and gold licenses are available either sequential for 1 CPU or parallel for 2 CPUs or more. And it is important to point out that in FEKO, we count the number of CPUs and not the number of cores. Thus, you can run a simulation with parallel process in a multi-core 1 CPU machine. For example, if you have a FEKO Gold sequential license in a machine with 1 CPU with 4 cores, you can have 4 parallel processes. Also, licenses can be not locked, floating, and we also offer the possibility to use dongle. We do have also GUI-only licenses for those configurations where the user wants to have one or several licenses to only prepare the model, set up and launch a simulation, and view the results, but being the simulation run in another machine. And here we would like to also mention that in FEKO Suite 7.0, all solvers are included in the same and unique package for one price as all of our previous releases. And these are the slides we wanted to share with you today to give an overview of what you will be able to enjoy in FEKO Suite 7.0. As usual, all the information of the new release will be available on our site. And also remember, you can request a 45-day free evaluation. And that said, I would like to thank you for your time and attention. Also, please keep in mind that on the 18th of June, we have our next webinar on electromagnetic field considerations in healthcare. You can register for this webinar in the link you have here. And also you can, and I would recommend you to have a look at all the other webinars we have on our website. You can just have a look at them by going there using this link. Okay, and this concludes our presentation today, and we could see if there are some, if time allows, we could check if we could see if there are any questions to answer.
Okay, great presentation. Thank you very much. We'll take a couple of quick questions, even though we're a little bit over time for those who want to hang on. That would be great. First question is, can FEKO model complex non-uniform dielectrics in its solutions?
Yes, we can. We can deal with complex non-uniform dielectrics. However, depending on the exact problem to be solved, there are different ways to do that. And this we would recommend the participant who has asked for this question to contact us directly or through our reseller, just to have a look at the problem and recommend the best approach to follow with FEKO.
Okay, and next question, can we use MLFMM for thick dielectric lens structure?
For the electric lens, you can use in fact MLFMM, but for these particular problems, we typically also recommend to have a look at the high frequency methods we have, and then try to also to compare MLFMM with one of our high frequency methods, to cross-validate the results and also to see which solver is better in terms also of runtime and in terms of memory requirements.
Okay, and there was also one about the cable analysis. They noticed the interior structure of the car was not modeled. Is it possible to convert captive files into CADFEKO?
Yes, I mean, just as I have explained, we do have a wide set of import filters, and one can just easily import a CATIA file in CADFEKO and then just work with directly in CADFEKO with the model already in CADFEKO.
Okay, great. I think that ends our questions. Since we have a few minutes over, we'll stop here, and I'd like to thank our presenter, Dr. Soler, and our sponsor, EMSS, for a great presentation today. You can find out more about their products on their website. Thank you for listening today.